Hi, my name is Ben Engber. I'm with a company called Thumbtack Technology. And I'm going to talk today about how to evaluate and compare NoSQL databases, especially on the operational kinds of traffic operational workloads. And this is one of those things that sounds like it's pretty easy to do. And the more you look into it, the harder it seems to be. And so this is something we as a company had allocated a lot of time to doing, made a lot of mistakes, and hope to give you guys a framework for how to understand, sort of how to focus on some of the more important things, because it's very easy to get distracted and focus on some of the less important things. This talk is sponsored by Aerospike, which is one of the NoSQL databases we use often. Some of the research in here was also sponsored by them, and a lot of it is independent as well. So try this. So just very quickly, let me just tell you a little bit about who we are to give you some context to all this. Thumbtack is a consulting company specializing in scalable application development. Like anyone who's working in scalability and trying to get horizontal scalability into their systems, scaling the data tier is a major challenge. And so before that NoSQL buzzword was a big thing, we spent a lot of effort trying to figure out ways to shard data and building sort of custom stores. But for us, as this NoSQL marketplace has developed, it's given us a great set of tools that allow us to do this more easily. So we jumped on this NoSQL bandwagon, very early, and we deployed it in many different contexts using many different products. More than that, like we have a team of about 50 engineers, the technical team of about 50. At any given point in time, we take some subset of those engineers and we do ongoing research and try to understand how the marketplace is evolving, what's going on under the covers here, and better ways to think about how to use these databases. And as NoSQL has become more and more mainstream, an increasingly large part of our business is companies coming to us and asking us to help them evaluate these kinds of technologies for their own use. So, I mean, the natural way to try and think about a product when you first go to evaluate a product is just to take a look at their websites and see what they're talking about. And right here, I've chosen just arbitrarily some features from the MongoDB website and some features from DataStax. And you can see they say things like, oh, we're scalable, we're flexible, and then we have all these nice things like dynamic queries and aggregation. But these things tend to fall into two kinds of categories that I think are not so helpful for actually making a decision that will be valuable in the long run. The first one is that scalability is actually a pretty complicated problem and can mean a lot of different things. And these databases sort of achieve scalability by trading off different things that are not so apparent until you really sort of dig in. And then from the other side, all these features around aggregation and so forth, this is such a rapidly evolving marketplace that by the time you make a decision based on these, it moves on. And probably you're not making decisions for any other kind of database based on current feature set. You're probably much more concerned about whether it can handle the load you need and is reliable. So I think in order to really get the right question for how to choose a NoSQL database, you have to go back and start asking, why are we even talking about this to begin with? Relational databases are great. We'll use them. We always will use them. So when customers come to us, the first thing I want to know is, why are you even thinking about this? And what we hear more than anything else is, because I've heard of it. Right? Now, that's actually not ridiculous, because you've probably heard of it for a reason, and the fact that you've heard of it means something's going on. It's a good reason to experiment, but it's not any kind of framework that you can evaluate these databases and make an informed decision. The next thing that comes up to us is, I want rapid application development. Now, we're a software engineering shop. I'm a big believer in agile and lean innovation. I'm all for any tool that reduces the cycles and lets us experiment and iterate more rapidly. When you get to the database, though, any decision you're making is data that you then have to live with. So all these guys who come out and say, we're going to give you really flexible schemas, if you go to any of their presentations, the first thing they'll say is, all right, this is how to model your schema. And so this is sort of it's a good way to do some prototyping, but as soon as you're talking about production use, it becomes a lot less valuable in this context because all that data is data you have to live with. Plus, it's not something that's really that easy to measure. And so really where people start to get really interested in this is in this whole big data thing. And big data is one of these highly overloaded terms that maybe it's not that big, and it's sort of hard to tell what people actually mean when they say big data. But one thing you can do is you can divide this kind of big data problem into two types of workloads. There's the analytic workload, which is sort of the standard Hadoop type problem. I've gathered a lot of data. I don't really know what it means. I'd like to investigate it more. I'd like to query it. But from a database perspective, what this really means is that you're iterating across large amounts of data with fairly complex queries, but you're not doing too much with it. In contrast, there's an operational workload, which is more along the lines of, we have a lot of transactions we need to handle. These transactions themselves tend to be relatively simple, but they tend to come in at really high scale. So for us at Thumbtack, we do a lot of work in ad tech, and that's sort of a classic example where even mid-sized players are getting billions of transactions a day. Well, trying to handle billions of transactions with a relational database is going to give you a real problem. But this problem's really everywhere. And I think one thing that NoSQL databases are opening up is, for industries all over the place, financial industries and gaming industries and so forth, there is a ton of operational traffic that could be captured that perhaps historically has not been captured because the tooling wasn't there. So in this talk, I'm going to be focusing very, very much on the operational side and how to handle that high transaction volume. So traditionally, when people have talked about the NoSQL databases, the operational NoSQL databases, they've grouped them into three kinds of categories. The key value stores like Aerospike and Couchbase, which were optimized against very, very high transaction loads. Things like, don't worry that it's blurry. It's blurry for a reason. Things like MongoDB for the document database, which takes this and provides sort of rich indexing capabilities. On top of this, allows you to query in interesting ways. And then column families like Cassandra and HBase. But as I said, I'm blurring this out because I think that this is sort of a misleading way to think about all of this. And it's misleading for a couple of reasons. The first reason is that this market is evolving so quickly. And so, for example, within the past year, the two major key value players, Couchbase and Aerospike, have both added secondary indexes and various types of other querying mechanisms onto their systems. So what is a key value store with additional queries on it? Well, it's sort of like storing documents. Maybe there's a little bit of different focus in between what features are exposed, but it's not that different, and these are rapidly converging. And I think, let's go back to the main idea of if we're looking for NoSQL for an operational database, the reason why we're probably looking here, right? If a relational database could handle it, we'd be using a relational database because they're well understood. Why on earth would we be investigating something new, experimental, not everybody knows it, unless we have a challenge that can't as easily be solved there. So, when we're talking about this NoSQL operational data, we're looking for things that can handle a very large number of transactions and can run in a cluster in a horizontally scalable way. And so the questions we really want to be answering here is, can it handle these large loads? Does the failover really work? What happens when nodes fail? And am I going to go crazy in operations trying to recover this system? And the key thing about all these types of questions is they go to the heart, not of the individual feature sets of the database, but the fundamental question of how do we handle that distributed key value? Can we do it at speed, and can we do it reliably in the face of failure? And so all these other queries that we talk about right here, queries about aggregation and so forth, if you think about it, these are just features layered on top of that core functionality. If we want to query a secondary index, well, sure, we'll look up an index, but all we're really doing is we're hitting every node in our cluster and then asking for a whole bunch of rows based on what those indexes return. And if you think about indexes themselves, what are indexes besides sort of ordered sets of keys and values? So again, very easy to write an application that uses exotic exotic queries, but also very easy to shoot yourself in the foot as you're doing that. So what I want to really focus here is how do these databases scale in the face of key value load? How are they achieving it? What kind of trade-offs are they making? And then once we have this, that'll give us a framework for building on top of it and understanding some of these other things. So when we first started doing this, we had a great plan. We were going to do a quick benchmark of every database in this market, or just a broad spectrum of databases. And we are going to use the Yahoo Cloud Serving benchmark, which can generate key value load. And then based on this sort of initial data, we were then going to have this great jumping off point for experimenting with really, really complicated stuff. But the nice thing was we were going to do this quick and easy thing right off the bat. And pretty early on, we realized that we were doing everything wrong. I mean, this sounds like one of those things that would be really quick to do. And it is. It's very quick to set up these systems and get them running in a cluster and generate load against them. But it's very hard to get data that's meaningful here, because each of these systems is making different trade-offs on different kinds of data properties to achieve the kinds of scales they're talking about. And so, aside from just setting them up correctly for the appropriate type of hardware and so forth, just in terms of the kind of reliability of the data and the type of consistency models, getting them into a state where it's even meaningful to compare them against each other is not an obvious thing to do. So does everyone here know about the Cap Theorem? Does anyone here not know about the Cap Theorem? OK, good, because I don't really want to talk about the Cap Theorem because it's one of these misleading heuristics, I think, that sort of gets in our way when we try to do what we want to do. So the basics, in case anyone's just being modest, is that you can choose, given that we're partition tolerant, because we are deploying this in a cluster, we can choose between consistency and availability. This is something that's been sort of just bandied around, and choose where you want to be on this consistent or available. And that was very popular for a long time in sort of these discussions on NoSQL. However, it's kind of misleading because, for one, consistency and availability as defined in the Cap Theorem is probably not what we're used to. It's kind of an academic notion that doesn't really match what we think about in terms of our application being available and so forth. And more than that, our applications themselves all tend to be a little bit consistent and a little bit available. Any application which uses a cache, which is most applications, has eventually consistent data in it. The HTTP protocol itself has your browser as an eventually consistent endpoint. And then more to the point, all these databases don't actually live in one place here. They all are tunable, often on a query-by-query basis, somewhere along this spectrum. So I think a much more useful way to think about these kinds of databases is not between consistency and availability, but between speed and reliability. And what does reliability mean? Well, it means different things for different kinds of databases, and it means different things for different kinds of applications. It can mean immediate consistency, but it can also mean things like tolerance of data loss in case a node goes down. Or it can be stronger versions of consistency beyond consistency, transaction isolation, as well as downtime. And each of these databases can live in multiple places on this speed reliability spectrum. So I mentioned our original plan. So aside from the sort of obvious problems that we sort of stumbled along, just for instance, getting YCSB to work at the scale we needed, we decided to dramatically simplify what we wanted to do. We took the initial set large number of databases, condensed it down to 4. Cassandra, MongoDB, Couchbase, and Aerospike. These were the 4 databases that we'd encountered the most in our neck of the woods in New York. And then we wanted to focus on creating very accurate baseline scenarios for each of them so that they could be meaningfully compared. Then our plan was we were going to get the raw performance for each of these kinds of reliability scenarios, and then we can move on to the other things like failover. So now I'm going to take a step back a bit, because in order to go into how these databases achieve the various types of trade-offs in terms of scalability, I need to go into a little bit about what they're doing under the covers. So what I'm going to be discussing here, I'm going to represent on these slides a series of 6 nodes, just representing a simple cluster. This cluster has a replication factor of 3, so each piece of data is stored on 3 separate servers. And then I'm going to be talking about what it's doing with various shards of data. Now, shards in this case, I just mean virtual shards, so that if a transaction might write in a row, that row lives in virtual shard A, just what's going on in those databases. And then I'm going to show you some of the trade-offs that different kinds of databases are making in order to achieve greater speed. What we know in general is all these databases, being based on key value type stuff, are giving up the ability to do joins across collections, but they're also making individual trade-offs even within that separate sharded key value space. So the easiest one of these to describe is the Masterslave Replication. It's easy because it's similar to how most of us work with relational databases all the time. And it's how MongoDB works. And at a basic level, if you want to write, all your reads and all your writes are going to a single master node for that shard of data. And the other nodes in the replica set are functioning simply as backups. The write returns as soon as it writes to the master. And since all writes and all reads are going to the master, you're guaranteed to be consistent all the time, even in your fastest level. Of course, what you're not guaranteed is that this data is going to stay there if that node fails. Since we're returning results before anything is replicated out to our replicas, we're making a durability trade-off here. And now, MongoDB allows you, of course, to inform your write to wait till it's hit disk or until it hits at least one replica. And that's how we'll get additional durability here at the expense of speed. Now, one thing that some of you might be thinking is that you can, of course, configure Mongo to allow reads from slaves. It actually does not speed anything up in our experience. It doesn't sort of fundamentally alter this trade-off. So the fastest capability we were able to get out of it is this top description. Something like Couchbase takes a similar approach, except that every node is a master for something. Couchbase stores its data in what they call V-buckets, but essentially every server is a master for some set of rows, and all, like in Mongo, all reads and writes always go against the master. So in every circumstance in Couchbase, you're guaranteed that consistent data. And again, like in Mongo, if that node goes down, you are going to lose data. So Couchbase also offers a more durable setting in a similar manner by being able to control when your write completes. You can request, again, whether it writes to disk or whether it writes to one or more replicas. And again, the trade-off is the same. These quorum systems, like Cassandra and React, are good examples, function in where every node is a master for every shard. And so the quick writes here allow you to write to any node that can accept this kind of data. And this is your classic eventual consistency model. If you have client 1 reading to someplace on shard A here and client 2 writing to someplace on shard A there, you have the potential for conflicts to emerge, and they have to be resolved typically by the last write wins. And you can exchange this type of behavior in a number of ways. When you write, you can request that your writer writes to every single copy of data before returning. And then, of course, you only need to read one to get a consistent copy of that data. You can do the converse. Always write to one node, but every time you read from all 3 and pick the one with the highest timestamp, which Cassandra does for you, and thus be guaranteed a consistent copy. Or meet in the middle, write to 2 and read from 2 and then pick the highest one and get a quorum there. And this is where we come up with the rule of thumb for these systems. If the number of reads and the number of writes is more than your total number of replicas, you're guaranteed to get some get immediate consistency. Any questions so far on where I am? Great. There's sort of a level beyond this. So databases like Aerospike and FoundationDB and now Cassandra 2.0 to some extent take the same approach, but then they provide an additional level of transaction isolation here to provide some level of ACID semantics to these types of transactions. And I'm going to go into sort of where this makes a difference in a bit. But the point is that there's another level of strongness and reliability that can be brought in. And again, all these things have overhead, so all these things hit you at some level. So just as a quick overview of where we are, there are systems like MongoDB and Couchbase. They're trading speed. They're always consistent, but they're trading speed for durability. Systems like Cassandra and React are trading speed for this eventual immediate consistency thing that we all know about from Cap. And then Aerospike and FoundationDB are doing the same kind of thing, but they also add this level of transaction isolation to provide some level of ACID semantics in here. So I'm going to take a step back and just focus on consistency a bit, because consistency as defined in these distributed systems is a little bit different from how we're used to thinking about relational data. And this is from the DataStax website. And it says that once a write completes, reads are guaranteed to get at least that write. And that's what we just described will meet that definition. But if you think about what's going on, if you can imagine the scenario where we're writing to every node in a cluster, and we're reading one, this is a consistent level in Cassandra. But if we're having a lot of reads, remember this write is sequential. And so we're getting dirty reads here very potentially. This is a read uncommitted isolation level. So we might read the old value, suddenly get a place where the new one has been written because the write is still in progress, and then get the old one again. And so maybe that's OK for your application, but maybe it's not. And this graph I have here, we tried to measure this, and it's one of these things that's a bit difficult to measure in the lab. So it appears to be an infrequent thing, but in this graph here, what we did is we messed with our cluster a bit. We introduced some latency in here. I think this was about 50 milliseconds of latency we introduced into our network. And suddenly we're getting 15 to as high as 30% of our reads, or high as 45% of our reads, are coming back dirty. And so this is where some of that acidity comes back into play. So one thing that Cassandra 2.0 is adding is it's using a consensus protocol. It's using Paxos to provide compare and set operations. All right? A compare and set operation gives you some level of consistency, of transaction isolation, and that allows you to do optimistic locking, for example, which was not an option there before. And then there's different levels along this acidity spectrum. Right? The next level up would be sort of a multi-key compare and set, which would allow us to perform sort of a financial transaction on transferring money from one account to another in one unit. And then the highest level is where we're used to in relational databases, these long-running transactions where we can submit multiple queries and have them all appear to commit at the same time. And this last one is where FoundationDB is positioning themselves. So I'm not going to spend a ton of time on this slide. My point here was that what we can do is we can sort of group, going back to trying to test our, get some benchmarks around this sort of thing, sort of group different levels of speed and reliability. So we have classes of speed without consistency, with consistency without durability, and then as reliable as we can make it. And so I can come back to this slide if you want to get there, but in the interest of time, I'm going to move on. What this boils down to is we ran a series of tests and we created two baselines for these databases to measure. One was as fast as we could possibly make everything. That's doing asynchronous replication, storing things as much in RAM as possible, using whatever consistency model was the fastest for the database and so forth. And then we put things in a reliable mode, guaranteeing consistency, and maybe even more. And once we got these databases set up with these parameters, then we could run some benchmarks that actually meant something. So we have papers that describe in excruciating detail what this actually means, and I can direct you to those. But this is how the test was set up. And then once we have these baselines in place, we're then able to construct some tests. So our initial set of benchmarking tests focused around these two scenarios. Essentially, load up a decent-sized data set, put it on SSD, put all the reliable semantics in place, and then bang it and see how it performed under as much load as we could give it, and then do the same thing for the fast scenario. All right, this is why Aerospike is sponsoring this talk. You can see one thing about Aerospike is the whole purpose of Aerospike is that they are highly optimized against SSDs. And so you could see here these balanced and read-heavy workloads. Read-heavy workload is 95% reads, 5% writes. Balanced is 50-50. But you could see that when operating in a reliable mode and going directly to disk with synchronous replication, they were able to really get a lot of traffic in through this, on the order of 200,000 for the balanced workload. And then on the other side, which is just optimized for speed, regardless of any reliable semantics, losing data if a node goes down, you could see these key value stores, the databases that have pitched themselves historically as key value stores, namely Aerospike and Couchbase, are completely dominant here and able to handle loads at 500,000 to 1 million transactions a second. This is with a 4-node cluster, by the way. So this is a very achievable, not particularly expensive configuration to get this kind of traffic through. From a latency perspective, again, I just want to show pretty quickly here that, again, the key value stores, these are the red and blue dots here, that even at the highest levels, we were looking at sub-millisecond latencies at these highest traffic levels. So what these databases absolutely succeeded in doing is getting very large numbers of transactions through for doing extremely simple things. So the next thing I wanted to do in order to evaluate that key value load is determine what this actually means. Obviously, it's great to get something in a lab where everything's functioning perfectly. So to try and make this a little bit more useful and determine, is this a viable way to distribute data in the real world, we decided to take clusters and then just mess with them. All right, so that means bring nodes down, gracefully turn them off, brutally kill them, put up firewalls in the middle of the network, introduce latency in the network, and just see what happens. And this is one of those things that's a little bit more difficult to quantify, but this picture up here shows what we would like to see. Right? So this red line on this graph shows the throughput of our cluster, the throughput of our system. And what we would expect to happen is that when we mess with our cluster, that cluster has some kind of outage for some period of time and then recovers. That's the whole promise of these kinds of systems. Right? And then we would hope that it will recover to full capacity. And then when a node rejoins, there's a lot of data rebalancing that needs to occur. There's replication that needs to occur. So we would expect another interruption here and again recover to capacity. And what we'd really like to see here is that these things, these gaps, are as small as we can make them. And that's, that they're small enough that we don't need to worry about them. All right, so in these graphs again, what you see here are the red lines are the throughput in operations per second of the cluster. Now in this graph here, we're just taking a cluster of 4 nodes here, and we are essentially obliterating it. We're just flooding it with traffic at its absolute maximum capacity, and then we're bringing a node down. Now I've got a million of these graphs. But I'm just going to focus on some interesting cases here. And what you see in this case is actually not super surprising. If you have 4 nodes and you're flooding it at capacity, and then you bring down one of the nodes, you would expect the system to suddenly have less capacity. And so what you're seeing here is, rather unsurprisingly, throughput goes down by 25%, and then when you add a node back, eventually goes up. Now you see some kind of effects here, but I think the most important thing to note is that the time of cluster outage is actually quite small. We're, again, running in our fast scenario. So this is, you'd expect it to be somewhat available in terms of the cluster. And you can see there certainly is replication traffic on the Couchbase side, but these systems tend to stay up. One other thing you'll notice here, by the way, is that the MongoDB scenario has essentially no change in throughput. And of course, that's because MongoDB has slaves sitting there doing nothing the whole time. So by definition, you have spare capacity. In these other ones, in this test, you haven't budgeted any spare capacity into your data center at all. So I think a more interesting test here is, imagine, forget running at full capacity. We're going to be running at this, in this kit test, we are putting in 75% of our available capacity. So this is with the assumption that if a node goes down, we should be able to barely handle all the traffic we're getting. Said a little bit differently, this is we've over-provisioned by 33% here. And our dream here is that the cluster functions, nothing happens in the case of a node failure. And of course, in all these systems, there is some brief outage while things are happening. But the nice thing about this picture is these outages are quite short, and these clusters come back online. And in fact, it's able to handle this load really very well. OK. Now, I'm now taking this failover traffic, and I am, instead of doing this in our as available as fast as possible, we're doing this with our reliable data set. This is the disk-backed data waiting for synchronous replication, all the good stuff I talked about earlier. But the same test is at 75% capacity. And you could see that the answer is quite different here of what goes on in this scenario. Yes, this is, well, we'll talk about the Cassandra in the middle in a second. But from Aerospike on top, yes, the cluster functions just fine when a node goes down. But when that node goes back up, if you think about the operational burden it needs to do, hundreds of millions of records have been written in that brief period of downtime. Remember, it's doing hundreds of thousands a second. And so when that node comes back up, all this data that is being written to other nodes needs to be rebalanced out. So a lot of replication activity needs to occur. And so you can see that the cluster does recover, but it's recovering, it's competing with your production traffic. And so the number is about 50% of the capacity you otherwise have. And so that's something that you need to consider in terms of your capacity planning at this level of reliability. In the case of Cassandra, this is sort of our classic not available scenario. When you have a 4-node cluster, if you want consistent, reliable data, you need to be writing both copies of your data with each write. If a node goes down, frankly, you're screwed. Right? You need to write to another data. Cassandra is not doing any automatic replacement of stuff, and your writes become just completely unavailable while this is down. So the right way to deal with this is let's talk about this quorum mode. Well, we brought a 6-node cluster in here with a replication factor of 3. As long as we can write 2 pieces, your cluster will be available. So this is sort of the traditional consistency availability trade-off made absolutely explicit here. The entire cluster becomes unavailable in that case. All right. What does this mean overall? Well, the good news is that all of these systems are able to function in the face of failure. all of these systems did recover exactly like they're supposed to, and we tried a lot of different ways to mess them up. Of course, a lab is a lab, and I'm sure production will find a way to really mess them up that we couldn't think of. But they were pretty much everything they did, they were able to recover in reasonable periods of time. This is in seconds. So, I think some of the really most peculiar things we did got as high as 30 seconds of downtime, but certainly faster than the sort of stuff you'd be doing with manual intervention. And on node restore, the complete unavailability, other than Mongo, which lasted about 30 seconds regularly, was almost immediate. Okay. So, just going back a bit in terms of takeaways of how to think about these systems and how to benchmark them. Right? The temptation when looking at these systems is by looking at that feature set. And those feature sets are valuable, and in fact, we have some studies coming up where we're doing tests of these secondary indexes. But testing those features is really extremely difficult to do until you're able to test these key value things. And the whole reason why we're looking at these databases is this failover capability, is this key value operational capability. And that's what we need to think about first. Next takeaway is that this speed reliability spectrum is really much more complicated than it seems when you talk about consistency and availability. And I think that this durability and consistency piece is becoming a little bit more understood, trying to determine when to go to disk and when to go to replicas. I actually didn't talk too much about this, but there's different types of node failures. There's node temporarily down, and there's node bursts into flame, right? So there's a spectrum even within this durability area. And so how to evaluate this reliability is really very application specific. It really depends what your application is trying to do, how much you care about losing a certain amount of data, and how much you care about consistency in various scenarios. So once you start thinking about this, then it gives you a context for making decisions about further features, about aggregation abilities, about querying by secondary index, and about doing time series kind of features that are coming in here. But these things are really essentially impossible to evaluate without doing this. All right, so that's actually ended up finishing, rushed through some things, ended up finishing a few minutes ahead of schedule. I wanted to make just a few statements about what it is. I sort of glossed over some of the methodology of this test. You can check it out at this link at the bottom. That controls all the tests in great detail, describes the methodology and the settings of these different things. And there's a ton more data both in these papers and aside from these papers. So if you want more explanation about some of the methodology behind this or some of the extra data, feel free to reach out to me. This is how I can be reached. The slides up here, I put them up on SlideShare so you could take a look or share them. Otherwise, I'm happy to answer any questions you might have.
So
yes?
I previously rolled out Cassandra in its early days, its pre-1.0 days. And one of the prime reasons for us doing it is that we were going from a sharded database in one data center to a multi-data center setup. So when we started examining how to replicate MySQL, etc., when we actually started looking at the database, we realized it was basically just a hash table and it was more suited to Cassandra. So I just wondered, in your evaluations, whether the multi-data center component actually figured in there.
Right. Yeah, so let's go back here a bit. So the question is, how does multi-data center replication factor into this whole discussion? And I'm going to go back here a bit, because I think this is really, this is a whole separate interesting thing. Like running one cluster when you have a very reliable network means that you're making these consistency trade-offs and speed trade-offs very easily. But as soon as you add a second data center into the mix, of course, speed of light comes into question, and there's no way you're getting 1 millisecond latency across another data center. So, the short answer is multiple data centers is when this eventual consistency absolutely comes into play. Now, it's not quite as simple as that, right? Because there's nothing in Cassandra that says you can't just simply wait until the other data center acknowledges the writes. You can still write to all nodes in all data centers. And then you're going to get A, big latency penalties, and B, you're going to get more of this performance, more of these dirty reads and so forth. And that's a lot of this dirty read graph here. A lot of this was sort of simulating multi-data centers, right? If we introduce a lot of latency into our cluster, we can isolate in our lab one cluster and make it look like it's another database, make it sporadically drop out, make it just very slow to respond. And again, I think in Cassandra, one nice thing about Cassandra is it's very easy to understand how it works operationally, so it's sort of easy to anticipate. Now, a whole piece of this discussion that I didn't really go into is, all right, let's say we want to have that maximum speed, and we want to have multi-data center masters, right? So that there's two types of eventual consistency. One is, most of our writes are going to one place, and eventually our other people are going to see it. The other is pure multi-master, multi-data center writes coming in at both data centers, in which case we get the standard conflict resolution. And what does conflict resolution mean? It's the same thing we do if we're writing applications with optimistic locking, right? We write an application with an optimistic lock, and then we want to submit our change. We get something back, and we say, uh-oh, the database changed from underneath us. You better do something to reconcile this. It becomes an application problem. And this ends up being true regardless. We can tell our database, sort of the default mechanism that many of these databases use is simply the most recent write wins. I think in Couchbase it's the most often written wins. But if you want to solve this in the general case, something like what React will do is it will return a copy of every change that's been made on both sides and let the application figure out what to do with all this information. Am I answering your question so far? Yeah. I think there's one last thing. I don't know if you guys have seen it, but the guys at React give a bunch of talks on these CRDTs. Any of you heard of these? So CRDTs, what they are, I actually don't remember what it stands for, but they're data types that function well in an eventually consistent environment. So, one example that Cassandra also supports is a counter, right? If we keep incrementing a counter, the two data centers might be out of sync, but eventually they'll converge because all we're doing is adding increments in place. It's not quite as simple as it sounds to do this because there's an ordering problem to make sure it happens well, but these are facilities that a database can provide. And there's other types of data types that can converge as well, not just increments, but add or subtracting certain amounts, set operations. There's a whole slew of these things. So, the short answer is that, eventually consistent arbitrary data will give you a problem no matter how you cut it, and your application needs to learn how to deal with it. But there are various kinds of types that allow you to do this much more easily as long as you're willing to limit your data to those types.
The way we got down it, we basically took a decision that the application servers in one data center would only talk to the local Cassandra node, the local Cassandra nodes. So we were replicating between data centers, so we achieved the aim of data center redundancy. If one data center went down, we had the full data set. But we didn't do cross writes from the application servers between the different Cassandra nodes.
Okay, so
Configure the application server to only read and write from the local nodes.
right. So I'm just going to repeat it for the. I think what you're saying is that you configure the local clients to only write to the local cluster, which is the typical way you do it, right? Because that's how you limit your latency the most. But if both data centers are being written, how did you handle the conflicts?
I think we did it online.
Okay.
It was eventual.
Right. So.
We lived with the eventual differences.
Yeah. Okay. So last write wins is a very simple heuristic to use, but I think the trade-offs are obvious. You can write to your database and be overwritten without anyone ever seeing your changes. It's always a little bit worrisome, and it's why we do optimistic locking to begin with on a web application. And then again, an awful lot of web applications don't do optimistic locking and just live with that reality. So it's something that might be just fine. Any other questions?
I have another one.
Okay.
So I don't know if it's still the case because I haven't looked at this stuff in a while, but there used to be a lot of controversy over what an ideal size of a cluster is, whether it's good to have big clusters, multiple small clusters, and this kind of thing. I think Aerospike, where there used to be Citrus Leaf, used to sort of recommend no more than 16 nodes in a cluster.
Right. Okay. So the question is, what is the optimal size of a cluster? And I have a few answers here. One answer is that testing really big clusters in a lab is an expensive proposition. So, it's one of the things, actually we're working on this right now, but it's one of those things where we like to have a hardware partner with us providing some of these resources, especially when we're doing tests against expensive things like SSDs. But a good rule of thumb, right, is that there's horizontally scalable is great to say in practice, but nothing's truly horizontally scalable. Nothing's really linear as you get larger. So from my perspective, you want your cluster to be as small as possible to serve the traffic you need. So multiple smaller clusters as an option gives you the same sharding problem you already have. Now you've got to manually shard against your multiple small clusters. So in my mind, that takes away a lot of the benefits of what you're trying to achieve using systems like this. I think it's also why databases like Aerospike and like Couchbase are compelling, at least to us, is that you can get a huge amount of traffic into a pretty small cluster size. Because one of those aspects of scalability, adding more nodes might be scalable in the technical sense, but you got to deal with those nodes, right? I mean, those are servers that you have to deal with. Failures are more common, and just more things to go wrong and more headaches. So that's my rule of thumb. What's the maximum that each of these databases can handle without completely blowing up is not information I was able to get. Yeah. Any other kind of questions? Any slides you might want to review or anything like that? All right, well, a few minutes early, so thank you very much.